Hi everyone, welcome to Python tutorials where we are focusing on image processing. In the last dozen or couple of dozen videos, you realize that we have been talking about traditional machine learning. We focused on image segmentation most of the time. We also looked at image classification, but we focused on traditional machine learning algorithms such as support vector machines and random forest and gradient boosting, okay, using XGBoost and also LightGBM. We also looked at feature selection, how to speed up our analysis, how to balance our data, right? So all of these are very important even for deep learning. We also looked at, for example, how to balance your data, right? And how to properly quantify the accuracy of semantic segmentation by using intersection over union, for example. All of those are going to be relevant even when it comes to deep learning because the challenges, the problems we are trying to solve with deep learning are the same. Semantic segmentation, image classification, and of course you can do a lot more, but given that our focus is on image processing, these are the two primary applications we'll be looking at. Now, starting this video, we will be looking at deep learning. Here, let's go through what deep learning is. What are artificial neural networks? What is convolutional neural network? Let's look at this terminology first. Let's get this done. And in the next one and the one after that and so on, let's tackle each subtopic until we understand exactly what every major terminology is as part of deep learning. And then let's go ahead and put together our own networks for image classification and semantic segmentation using UNets. All of this is very easy. It may sound difficult if you haven't gotten your feet wet, but I'll help you get your feet wet so you can actually get a bit more comfortable with this terminology and also putting together your own code to do to handle this deep learning and CNN type of networks. Okay, now without delaying, let's actually go through understanding what deep learning is. But before that, let's go ahead and look at traditional machine learning because this is our comfort zone. We looked at this the last 12, 20 videos, I should say. So for traditional machine learning, we have our images, we have our mask, right? Corresponding mask. Again, go to appear.com to annotate your own masks. So in this case, we have these. And then we extracted features from these images by applying various filters. In fact, in the last video where we did feature selection, we looked at, of all of these features, only 6 mattered. All the remaining ones, like we had 41 to begin with, all the remaining ones did not even contribute a lot towards our building this model. Okay, so with traditional machine learning, you better be good at feature engineering, meaning understand what features work very well with your data. If not, you'll throw 1,000 features and then you'll get 100 features out of those that are useful, and then you can use those. That's nothing wrong with that, but is there a better way, right? That's the whole question. Okay, so we extracted features and we converted them into like single columns. And we used a classifier. That classifier could be random forest. That classifier could be support vector machine, gradient boosting. We did this in the last few videos. Now the question is, how do we know which ones work, right? So we looked at some of these Gabor features. So these are the Gabor kernels. If I go back, again, if you don't know what I'm talking about, go watch the one of the previous videos on this topic. Gabor is just a kernel. It helps us define these different features. So as you see, this is like a bandpass, yeah, filter. We are applying this convolution onto the original image to get a response that looks like this. This is the next filter. This is the next filter. We constructed all of these by changing the theta, sigma, gamma, and all of these, like aspect ratios and everything. The question is there a way, instead of building features, okay, with predefined equations, let's say, instead of doing that, can we actually learn the features? I hope it makes sense to you. Okay, we know that this one works very well in detecting the zebra because you see all the lines are kind of horizontal, and then something with my 45-degree tilt is going to highlight this feature very well, right? But we are looking at this in retrospect and saying, oh, that worked very well. But can I actually take this input image and corresponding mask, which is my ground truth, and build features that actually work well for this problem? This is deep learning in a nutshell to you, where features are learned on each iteration, right? And what happens in this each iteration? You're minimizing a loss function. I talked about this again a couple of videos ago. You have a loss function. your true mask or true values, your predicted values. What is the difference between them? And can I minimize the difference between them by updating the weights? Okay, this is the core essence of machine learning. This is the core essence of deep learning, convolutional neural, whatever the networks you are talking about. Now let's get to the next level. Okay, so as I mentioned here, good features should highlight the useful attributes. And the whole point here is, how do we identify these features? And the question I'm asking is, can we build these features? They work for this simple, but what if the problem becomes even more complex? For a simple, okay, you have a nuclei and background, a simple, histogram by segmentation is fine. But what happens, on complex data with a busy background? How can you do that? Now, if you look at this busy slide, on the left-hand side, let's start from here, right? If your problem is only separating these features from the background, then a simple Otsu thresholding is fine. Okay, you only need one parameter to do this, which is where is my threshold, and separate the background from the peak. But your problem is a bit difficult. You see some fine structures there against the background. One parameter is not enough. Now you have to train hundreds of parameters. This is exactly what we have done with our feature extraction here. We extracted 40 in this case, but you probably need hundreds of these to get it right. That's exactly what we mean here. You need hundreds of features, which we can handle with traditional machine learning. You can generate hundreds of these features and then train a machine learning algorithm to do these type of problems. And more than 90% of image analysis when it comes to microscopy or scientific data can be achieved using traditional machine learning. So please look at XGBoost and LightGBM and Random Forest and feature extraction as your first choice, especially if you have limited training data. If you have the luxury of a lot of training data, hundreds if not thousands of images, then we can start attacking some of these tougher problems where you have, for example, in this case, mitochondria against busy background, or multiple classes where you have a lot of overlap going on. You see, you can't even tell the difference between this region up here and the other region over there. So advanced machine learning can definitely help in those cases, right? So this is where deep learning really helps. And again, I put this as feature learning. Now we are actually learning how to build the best features. Okay, so now we're slowly progressing in understanding the need for deep learning, what deep learning is, and like I said, after a few of these tutorials, hopefully you should have enough information in terms of understanding the core concept of deep learning. Once you understand that, then you can read any paper and everything makes sense to you. Otherwise, it may sound like Greek and Latin. Okay. So now, what is deep learning? Let's say I took this mitochondria image, right? Let's take a small piece and let's look at that. Like, how do we identify this as mitochondria? What's going on here? First of all, think of this deep learning as you have different layers, and it's deep because you're going deep into these layers. Okay. If you only have one layer or two layers, then that's not deep. If you have at least one or two of these layers, then it is deep. Now you may be thinking, what in the world is layers? We'll get to that in a minute. But first, think of the input layer as all the pixel values. So in this case, I have 1, 2, 3, 4, 5. My image has 5 pixels. So these are the 5 pixels. Okay, think of this. So in this case, this image may be 16 by 16, right? So you have 16 multiplied by 16, like you have 256 of these input pixels. What happens next? Well, we are connecting each of this pixel value or node or a neuron. I'll explain this in a minute. This is where the neural network comes into the picture. Each of this to all of these neurons that are hidden in the layer number 2. So layer number 1 is only pixel values. Layer number 2, think of these as filters. Okay, think of these as filters. So I have these many filters, and each pixel is going to each filter. Okay, or each neuron is the right terminology. These are all artificial neuron. What does a neuron do? A neuron has an input, and it takes in the input, and it decides whether it should give an output or not, whether it should fire or not. An actual neuron does that. It takes in information and it's like, shall I pass it on or not, right? That's what an artificial neuron does. Takes an input, shall I pass it on or not? So at this point, all of these neurons are getting inputs. Now they decide whether I should pass it on or not to all of the neurons in the next layer. It doesn't have to be all of the neurons in the next layer. It can, we can basically say, okay, don't drop out 20% of this randomly. So only 20% are connected. This is advanced stuff that we'll get to later on. But the whole point here is there is an input layer, and from each of this neuron in the input layer, which is in our case is a pixel value, let's say, it's connected to all of the other hidden neurons. It's hidden because it's not outside, it's inside. This is the hidden layer number 1. This is the hidden layer number 2. This is the hidden layer number 3. So you can put any number of hidden layers, and there is something called too deep. Yeah, you don't want it. You don't want that. Sometimes you may run into some problems. We'll again understand all of these later on. But first, understand what deep learning is. It's deep because you have different layers. Information is passed through different layers. Why? We'll see that in a minute. So at this point, we can say, okay, this is deep enough. Now let's send all of these to output layer. My output layer has 3 outputs because in this problem, I built this problem such a way that I'm feeding my neural network with 3 different types, 3 different classes of images. One class is lipids, the other one is mitochondria, the other one is lysosomes. These are the 3 images. Think of this as for non-biologists, okay? You're trying to do dog, a cat, and a cow. 3 different things. Feeding this. And you're also telling it what the right answer is, right? Because you're feeding a dog and you're saying, hey, this is a dog. This is a mitochondria. Hey, this is a mitochondria. So it actually learns based on what you're saying here and then updates these filters until it gets the right answer. Okay, now one layer of understanding. Let's get to the next layer. These are all the multiple hidden layers. Why do we have multiple hidden layers? Because each layer understands, or each layer, think of these as filters. They understand different types of features. Yeah, when you have edge detection, it clearly highlights the edges. When you have, for example, a median filter, it shows you a different type of information about your pixel values. So think of these as very similar. Each layer is giving you different type of information. So this is a hierarchical feature representation. I'll give you an example what that means. So the first one, layer, it learns the pixel values. Right? In this case, we're supplying the pixel values, so there's nothing to learn, but it knows the pixel values. The next layer here, it will learn the higher order features like, okay, straight lines. It learns to detect straight lines. If you're training this on a bunch of human faces, this is where it learns to detect, for example, rounded features versus straight features, for example. Okay. The next layer is where it starts to combine some of these straight edges into some shapes. And the next layer, it identifies certain features because it's combining some of these edges, and then it learns some of the actual features. Oh, this is an eye. This is an ear. Yeah, this is like hair, and this is your nose, and those are the things that are identified here. And then finally, it identifies the combination of features. Oh, these are eyes. This is in mouth and nose and hair. Oh, this must be a human, right? So that's what happens at the output layer, and then it gives out a probability of saying, hey, human. This is 98%. This is human, but cats also have noses and eyes and, some similar features. So I think this is 0.5% cat and 0.2% something else, right? So it gives you all of that. And then you say, oh, because this is 92% mitochondria, in this example, I'm going to say this is mitochondria. So deep learning, it's deep because you have different layers that go deep. In this example, I'm showing you only what they call artificial neurons. Okay. Other terminology used for this is multi-layer perceptrons, MLP. So whenever you see papers, when you read these, published papers, look for these terms: artificial neural network, multi-layer perceptrons. These are all like artificial neurons. Okay. Again, input layer, output layer. Very clear. Inputs are pixels in our case because we are dealing with images. It can be anything. It doesn't have to be just images. Yeah. Input layer has a bunch of values, and those values get transferred to the next layer and the next layer and next layer. And finally, you have a few output layers giving you the probability. Now let's look a bit deeper into what let's pick one neuron, like right here. Okay, what's going on? It's getting information from the previous layer, right? In this case, this is input layer. It's getting some information and then it's passing on some information. Let's zoom in a bit. Okay, now let's look at pixel value 1, 2, 3, 4, and 5, right? This X is input. We always give X as input, Y as your output, right? So let's stick with the convention. X1, X2, X3, X4, X5 are input. Now, what do we mean by this from a mathematical point of view? All the inputs are connected to this neuron. What does that mean? When we say that, that's basically at this point, this neuron is taking this input pixel value, multiplying it with some weight. And how are these weights given? When you just start your neural network training, these weights can be assigned at random. Or these weights can come from a trained model that has already been trained in the past. So there is some starting value. But either way, there are some weights that are either randomly assigned or assigned from importing some other previous trained model. Okay, so far so good, I hope. But these are some weights, which is nothing but some numbers. If the weight is 0.99, I know that this pixel is very important. If the weight is 0.00001, I know this pixel is not important. That's what these weights are. Okay, actual values. Think of them as values between 0 to 1 to make things easy. So these are inputs, these are weights. What happens at this neuron? The neuron is just doing the math. Artificial neuron is basically doing math. It's actually multiplying your X1 with W1, adding it to X2 multiplied by W2, X3 multiplied by W3, and so on. And of course, I added a term called bias, and it adds an external term called bias. Okay, let's again understand this. This neuron is computing the weighted sum of all of these inputs from the previous layer. Okay, and adding something called bias on top of it. Now, as part of your neural network training, you're updating these weights and this bias value. Bias is basically, okay, I did all of this, plus I want to add some extra constant. That's what bias is, okay? Think of this in a mathematical way, everything makes sense. This is very important. Understanding artificial neuron is very important to the entire deep learning or neural network, obviously, right? So let's spend one more minute in looking at this. This is our computation, where it's taking the previous values that are all connected to this neuron, multiplying them by weights, and adding a bias to it. And these weights and bias, they get updated every time you go through your neural network training. How are they updated? Well, initial weights and bias, and then it goes through and then it says, oh, this is a cat, right? No, this is a mitochondria. So go back and update the weights. Oh, this is a lipid. Well, getting close, but not mitochondria. Go update the weights until you get it correct. So it's an iterative process using multiple training images and multiple training masks. Okay. Now, what is the output? The output doesn't just go directly to the next neuron. Okay. In fact, what I showed you here, the output going to the next neuron, right? I mean, we just looked at one neuron here, but the output is not just going to the next one. There is something called activation function. I'll talk about all of this again, so don't worry if you don't get everything in one go, okay? So we are doing math here. We are adding bias. What happens next? Next comes activation function, which means, okay, there is an output, but how do we know whether we should transmit that information or we should not transmit that information, right? That's what our actual neuron does. Hey, you get some information. Shall I fire it up or shall I not fire it up so I connect to the next neuron, right? So the activation function controls that. And activation function can be a straight line, which is a linear activation function, which means if the output of this entire thing is 0.5, or let's say 0.8 to make things easy. So if the output of this is 0.8, and if you have a linear activation function, then you're just multiplying it by 1, then you get 0.8 as output. So when you say identity function, for example, that means it's not doing anything. That means everything that goes in, you transmit to the next one. There are many of these activation functions. Like this is called a classic sigmoid activation function, right? So if the value is above, for example, 0.5, transmit. If it's below 0.5, don't transmit. Okay, so I mean, I just described a step function, but a sigmoid, we'll get to that later on. So after this, you have your output to other neurons or hidden neurons. I hope this makes sense. You have your neuron, bunch of information coming in, you multiply those with weights, add them, add the bias, and see if the final value that you go through this activation filter or activation function. And if it goes through, it connects to the next neuron, which means the next neuron gets the information from the previous neurons after activation and then transmits. This is how the neural network is actually built. I hope this makes sense. And like I said, as part of our training, because for training, this is all supervised training I'm talking about. As part of our training, we're providing a bunch of raw data with the labels saying this is a cat, this is a dog, this is a cow. So it learns from these and it updates these weights. And updating the weights is nothing but building your filters or learning the filters. This is why I said, what if you can learn the filters or features? This is how it actually does that. Now, let's look at convolutional neural networks, because this is a artificial neural network, or in some cases they call these fully connected neural network or dense layers. Okay, I'm giving you a lot of terminology which I'll explain in detail in the upcoming tutorials anyway. Okay, so now let's understand convolutional neural networks. But let's quickly look at what convolution means, and you probably should know this because we covered this in many of our videos in the past. You have a digital image. When you zoom in, the digital image looks like this, right? I mean, you have a bunch of pixels. And convolution is just pixel math. How do we do this math? If you have the pixel values like this, and if you apply a kernel, for example, like this, again, think of these as weights. My weights here are -1, 0, 1, 2, 1, 2, 1, -2, 0. We called it kernels before. You can think of those as kernels, but whatever. You have this matrix and you multiply it with this. What do you get? 170 times -1, 245 times 0, right? So you do all of this, you get a value of 394. So you replace the central pixel with a value of 394. This is a convolution operation. So convolutional neural networks are completely based on this. So in convolutional neural networks, you have convolution layers and you have something called pooling layers, which I'll talk about in a second. And stride is, okay, you're done with convolution here. By how much do you want to move? Stride 1 or stride 2, right? 1 means move by 1 step, 2 is 2 steps. It's very simple to understand there. That's our stride. Now, finally, understanding the pooling. What is pooling? Let's again look at, this is my pixel values. And now I have a 2x2 kernel, right? 2x2 right here. A 2x2 kernel. I apply that right here. Max pooling is basically, hey, look at this 2x2 window and tell me what the maximum value is. In this case, the maximum value is 121. So just put 121 there. In these 4, and by the way, we are stride, in this example, stride is 2, which means I'm moving from here by 2 spots. So I'm moving to here, right? So here the max is 212. And down here, the maximum is 27. Down here, the maximum is 78. There you go. So after max pooling, your size decreases, right, of the image. Let's say this is the filtered image. And after max pooling, the size went down by 1/4 in this case. Okay. So this is max pooling. Why am I explaining this? Now let's look at convolution neural network. You probably saw these type of images many times. So what happens in convolution image? You have an input image and you have a whole bunch of filters. This is very similar to what we have done with random forest. Think of the first one as your Gabor filter 1, Gabor 2, Gabor 3, Gabor 4, and the next one is your Gaussian filter with sigma 3, Gaussian filter sigma 7, edge filters, and so on. So how many filters do you have? You can define that. Hey, how many filters do you want in layer 1, layer 2, layer 3? Okay, so let's say we have like 32 of these. So which means one image becomes 32 filtered images after your initial convolution action. And then you're doing pooling. Okay, let's say you're doing, again, pooling is this. You go from, in this example, 16 total pixels to 4 pixels because we are doing 2x2 kernel with a stride of 2. Okay, so let's say you do that. That means your image size goes down here. And also the number of filters, you can define how many. And again, you do pooling. Size goes down. So it depends on how many ever you want to do. And at the end of it, you take all of these images, convert them into a single vector, flattened vector. Remember, for our neural network, what goes in is a flattened vector. It cannot work with 2-dimensional images or multi-dimensional images. It only works with 1-dimensional array, as you can see here. So we convert this into a 1-dimensional array. These convolution layers can also be 3D, not just 2D. Okay, so the idea is you generate a whole bunch of filters, and the next you are doing pooling, and the next you are doing pooling, and then you convert that into a flattened vector. Okay, this part we just talked about it. We know exactly what that is. And finally, you apply some sort of an activation, and then you get the probabilities of this input image being a mitochondria or lipid or a lysosome. Okay, so now if you look at these, this part, this is all feature maps. These are all features. So all of these convolution layers, think of these as features, because what is a Gaussian filter? It's basically a kernel with a whole bunch of values in the shape of a Gaussian, right? So these are features, but obviously not Gaussian, but random initial weights. As we go through training, the weights get updated. So the features actually learn to be good features to detect this, these type of mitochondria. I hope this makes sense. So this part is feature maps. This part is the classification part. Okay, this part. Now, these are all the convolution layers we're talking about, and these are the dense layers. Okay, where all neurons are connected to each other. So just like dense layers, we talked about how dense layers, the weights and biases, you have exactly the similar structure going on for convolution layers. The weights and biases are all learned during the training process. Okay, so that's exactly why I'm referring to this as feature learning. You're learning these features. Okay, now I'll take a couple minutes time and then actually continue in the next video, but I just want to show you how easy it is to put together this code. So in this case, we are only using the dense layer, which means I'm just defining this part. Okay, you don't need all of these unless you're working with images. If you're just working with structured data, even simple images, the standard dense layers can help you in image classification or any classification. So how do you define? In Keras, there is something called sequential. Okay, you import the sequential in keras.layers. Keras is the library we are going to use for the rest of these because it makes it easy for people like us, researchers, who are not advanced coders, to kind of put together this type of code. So we are going to look at keras.layers. We are importing the dense layer, convolution layer, max pooling layer, everything. Someone else did a great job writing all these libraries, so we just call them. So how do you put together a dense layers only neural network? Here you define, okay, I want 12 neurons in the dense layer, 8 neurons in the next layer, and 1 neuron as output, because it's only binary output, yes or no. Okay, and if it is a convolution layer, again, this may look like too much, but if you look at this, okay, sequentially, I would like to add first convolution 2D of size 32, okay, and input shape is 28 by 28 by 1, and activation, I'm using rectified linear unit. We'll talk about activations later on, but this is the activation. So after this layer, it's multiplying or it's going through this ReLU layer, and then anything that passes this is going to the next thing, which is the max pooling. Okay, and after that, let's drop out 20% of the neurons, and then the next layer, 64 filters, 3x3 kernel, activation, ReLU, and so on. Okay, and you keep adding multiple convolution layers. So you just saw 1, 2, 3 convolution layers, and you flatten. You have to. Again, remember, this is our vector. So flatten all of this two-dimensional information right there, and then go into dense layers with 128 neurons, activation ReLU, and finally output 25 neurons with activation softmax. In this example, this can detect 25 different classes and gives out a probability of each class. That's exactly what this is doing. And in addition to this, there is, you compile, once you define this, you compile the model using some of these terminology like loss function, optimizer, and metrics, right? We talked about loss function. Traditional machine learning, deep learning, you have to minimize the loss function, something that represents how accurate you are, in terms of your model. And optimizer is something that helps you minimize the loss function. Gradient descent is an example. We'll talk about that. Metrics. What metrics do you want to keep track of while we are training? Accuracy, because this is a classification problem. If this is a semantic segmentation, maybe intersection over union is a good metric to keep track of. But as you can see, everything makes sense. So in the upcoming videos, like I mentioned, a bulk of your time will be spent in getting the data ready, but then writing this can be very, very, very easy. And In fact, you don't even have to write any of this. Someone already did that and published papers and published the code, so we can just take one of the existing models. There's many existing models out there. You probably heard of VGG 16, 13, 16 and 19 are very popular. And some of the recent ones like ResNet, where is ResNet? Right there. ResNet 34 is also very famous. What do I mean by VGG 16 or 19? Well, it's basically architecture. For VGG 16, it says, okay, 3x3 convolution plus ReLU activation, 3x3 convolution plus ReLU, and then do max pooling, and the next block, and so on. So this is just an architecture that got put together. Okay. Now, some of these are trained on millions of images, and you already can start with those weights. Remember when I said, okay, the initial weights can be random, or you can import from pre-trained weights. So VGG16 has been trained on millions of images from ImageNet database. I think it's millions of images from ImageNet database, which means it already has weights that got trained on these images. So it knows how to detect these straight lines and roundedness and all of these textures and everything from these. So instead of starting from randomly distributed weights, you can start from this. This is exactly what we call transfer learning, where you already trained something for a different application up to a certain point, and you take that and further customize it for your specific job. We will focus on this again as part of these tutorials. Like I said, I promise if you follow these tutorials, you should be able to be a bit more comfortable in understanding, not only understanding the terminology when you read papers, but in putting together your own code, which is the ultimate goal of these video series. So what are we going to do in the upcoming videos? First of all, in the next two videos, I want you to get hands-on experience in terms of putting together a neural network and defining a problem, right? Okay, you have, for example, breast cancer data set that's out there, and you can use public data where you have a whole bunch of features, attributes, and then whether a person with that attribute, whether that has been diagnosed as benign or malignant, okay? So we can put together a very easy way to put together this, and then let's do that in the next one. And the video after that, let's actually put together a quick image classifier. Classify this as a dog, a cat, or something. Okay, that gives you a good hands-on experience in terms of, at least minimize your any fear that you have about this. And then once you do that, you will run into some terminology that we have to understand, which is activation function, which we already looked at, loss functions, optimizers, backpropagation, scaling, dropout, batch normalization, batch size. There are a lot of terms that may sound intimidating but are very, very straightforward. So let's spend maybe covering 2 or 3 of these in each of the videos in the upcoming sessions. And like I said, at the end of this, you should be able to be a bit more comfortable with this deep learning topic. So I hope this sounds like a good plan to you. If you have any other questions or ideas, please leave those in the comments. Please don't ask for any advanced stuff, because these are going as a course, as you can see, primarily targeted to people who are not familiar with deep learning. Once we get to units and others, then we can discuss some advanced stuff. So I hope you found these tutorials to be useful. Again, please go ahead and subscribe so you are notified whenever new videos are uploaded or made available as part of this channel. So thank you very much.